Yep. Chris, you can start.
All right. Yeah, thank you for the nice introduction. Yeah, so I'm Chris Rackauckas, MIT, Pumas AI, and Julia Computing. They all factor in towards this kind of general goal of learning models that extrapolate well. So today what I'm going to be talking about is specifically learning epidemic models that extrapolate. So an outline is going to be that first I'm just going to be talking about scientific machine learning and its impact on epidemic modeling, and then I'm going to go into the actual scientific machine learning software and some of the techniques and things that you can use it for, and then kind of explain like what kinds of what is the class of problems that's able to solve, and why is it an advance from the parameter estimation techniques of before. So, so the basis of this talk, though, if there's one thing that you kind of take away, it's really that scientific machine learning is this idea of model-based data efficient machine learning, right? So, you have machine learning that's fully based off of data, and you have mechanistic modeling, and people kind of put them in two different worlds. But with scientific machine learning, what we're really doing is we're mixing models with data, right? We're basically saying there's an amount of knowledge that we need to have. And if we hit that requisite amount of knowledge, then we'll get to good predictions. And we don't care really if the knowledge has to come from models, right? Like models are generated from many different experiments. And so they're kind of a source of data themselves, right? So we can mix these with data. And if we do this effectively, we should be able to do better than if we only did one or the other. Right. So this is like the overarching goal of the entire talk, just to kind of show that this idea holds true in epidemic modeling. So the way that we do a lot of this epidemic modeling is through what's known as the universal differential equation. So here is like the highest level overview of a universal differential equation. I'm going to go into one example kind of deep first before we kind of walk out and see a lot of the examples of how this is actually working in practice. So like the high level overview though is you have a differential equation and you have part of it defined by a neural network. Why a neural network? Well, it's just some kind of thing that can represent any possible missing function, because neural networks are universal function approximators, right? And so you can specify like, hey, this is the mechanism that I know. I know that there is some linear relationship where if I leave bunnies alone, they'll grow exponentially. If I leave wolves alone, they will die exponentially, right? But there's something else going on in the system. So please tell me what the rest of the system must be doing, right? And so what the universal differential equation approach lets you do is you can find these missing functions within any given kind of functional or any kind of simulatable space. And once you've found this unknown relationship, you can do a symbolic regression and actually recover what the missing model is, right? So you can use all of the mechanisms that you know. You can use everything that you know about physics, biology, etc., and basically just say, let the neural network learn what is that missing higher order thing that needs to tick in order for us to actually make this prediction correctly, right? And then that's the general idea behind machine learning. It's the skeptics form of machine learning, right? It's machine learning for those who want to do the least amount of machine learning possible and the most amount of modeling, right? You can also take this to another level, and I won't be mentioning too much about this specific technique, but one thing that you can do is you can also do this in a Bayesian form. So you can say, train this neural network inside of a differential equation using, using probabilistic programming languages and adjoints through them, which I'll discuss at the end. And what you actually get when you do this is you get a probability distribution over neural networks that represent possible missing functions in your model. And then you can sparsify it and say, well, what is the probability of having this symbolic term in my model? And then you can turn it down to, after you do some sparsity terms, you can see, when I have my sparsity parameter at this level, the only thing that shows up is quadratic terms, right? Maybe there's some error in the coefficient, but what this tells me is that no matter, the fit model seems to only be able to be described in a low dimensional form by adding a one quadratic term for this missing part of the model. So most likely what I was missing in my model was a quadratic term, right? So, this is kind of like the high level overview of the method, but let me kind of show an example of why you want to do this instead of straight machine learning. So let's a little bit. Let's take a neural ODE and let's take a epidemic model, right? So just like a straight, it's a form of SEIR, and we take some data from it, and we want to ask, can we learn a model that is actually giving us interesting or good predictions, right? And so here I'm only going to train it from day 0 to 21, so 3 weeks of data, and then we extrapolate it forward. And here this is with the neural ODE, right? This is like some neural network embedded inside a differential equation where we're letting the neural network try to be all of the information, right? So U prime equals a neural network, Y neural network, because it can represent any possible function. And so this is like a representation of any possible dynamical system. And with 21 days worth of data, you can see that the prediction doesn't do so well, right? It just doesn't learn the asymptotic properties that we would expect a epidemic model to have. None of that information is in there. You can't expect, if you have a line moving slowly up like this, that it's going to know that it's actually an exponential, right? But okay. What about this universal differential equation approach, right? What you can do is you can say, well, I have this bigger model. I know that SEIRs are kind of true, but what I don't know about this model is how exposure works, because it couldn't have actually the model that generated the data has a pretty eccentric exposure term, right? Because they're trying to model how masks are working, like whether people wear masks, whether people care about social distancing in the United States and certain per state and everything. And so actually knowing how to model the exposure term can be something that's highly nonlinear. But a lot of the other parts of the model you can get very easily, right? You can know that if someone is infected, how many days does it take for them to recover? And if what percentage of people are hospitalized versus not hospitalized? That tells you whether they go to I versus D, right? So this is, SEIR model with hospitalization, where we've now extended it to say the exposure term, the term that we have the most uncertainty in, let's let that be a neural network. And when you do that, what you see is that, even with just 21 days worth of data, you're able to then extrapolate about, maybe another week or two fairly well, because there's just a lot less that the neural network has to actually learn in this model, right? We've kind of given it a nudge to being epidemic model-like, and just saying, well, you need to learn what's nonlinear in here, knowing that the basics of an epidemic are true, right? We can actually do even better than this, right? So, one thing that you might want to think about is, well, could we actually just directly learn all of the symbolic equations from the data, right? And you can attempt that. And so there's these methods like Cindy, but the issue with some of these methods is that they can require a lot of data to do correctly, right? So if you run Cindy on this example, what we actually get is just like a mess of coefficients that don't necessarily go to 0, just because it's not able to, there's not enough data. Usually we find that Cindy techniques require 100, 200, or 300. It requires in the hundreds of data points, not 21, right? 21 data points is insane to do machine learning with and expect to learn everything correctly in a way that extrapolates. But what if we put these ideas together, right? So what if we say, well, we learned this neural network, right? This neural network covers this unknown dynamical system. And then after we've learned a neural network, we have a function, and we can actually take that function and we could perform sparse regression on it, right? So we can take sample inputs, get sample outputs. We can take, it's a neural network, so we can put as many numbers in as we want, take as many numbers out as we want. You have to make sure you sample in the region that is, where you've trained it well enough. But if you do that, then what it says is what you're missing is, a linear term, quadratic term, and something semi-cubic. And when it extrapolates out, it is getting a much better extrapolation. Now, why is that the case? There's a lot of reasons that you can use to explain this. One is that lower dimensional behaviors actually, it's a nice numerical analysis result that in lower dimensional polynomials extrapolate with less error. There's a lot of other ways that you can kind of explain this kind of property. But what you're basically doing is you're saying we are using the neural network as an intermediate to be able to learn, missing functions within simulations and such, and then we can pull them out and start to regress them and kind of figure out, what did we learn right here? What could have been missing? And when you then pull it down to a sparser form, then you get something that can extrapolate fairly well. And this is like, this is a simplified form on some generated data, just to be able to say, oh, does it work out well? Yes, it does work out, and it gives you the results that you'd expect. And so then we take this and we take this to real epidemic data to start looking at using this in practice, right? So one of the papers on this is from Cell Patterns. This one is kind of one of the earliest papers that we did on what we call the QSIR in this diagnostic for quarantine. And the basic idea here is that we take a SAR model, right? And we say, SAR models are what they're really missing is they don't have a sense of when people leave the infected population or are not possible to be in the infected population because they're part of quarantine, right? I mean, oversimplification, yes, but maybe we can capture a lot of information just by saying, let's learn how quarantine works and add this to an epidemic model. But now quarantine is going to be different for every single state, right? So when we're looking at, COVID's first starting out, some states were more reluctant to have, to send people to quarantine. Other states or other countries were just completely open for the first few months and just let COVID run wild, right? So this is going to be something that changes country by country or state by state. So then this has to, this is the real question then, right? If we actually to do this kind of model and we learn what the quarantine term is by saying it's some neural network based off of the other states, right? If we learn this relationship for a given country and its quarantine, does it actually kind of give us some information about the country that it was from, right? Could this be a diagnostic for how to kind of measure the quarantine of a given country, given its information about the susceptible, infected, and recovered, right? And when you do this process, well, you can actually then plot, Q of t as this variable that you've now learned, represented through the neural network. And what you see is that if you go country to country to country, like I had a grad student, actually check, a bunch of these different examples. And what you see is that where the inflection point in the quarantine is actually occurring is actually where, you can line it up almost within a day or two of where the actual quarantine was initiated for a lot of these countries. So, in Spain and Italy, and if you go country to country, that ends up being the case. And so, this simple SIR model where you're saying, oh, quarantine accounts for the things that makes SIR wrong here, it is an oversimplification. But then if you double check it against, a bunch of these, countries' data, what you see is that it's actually capturing something that seems quite realistic, right? So then we began to ask a lot of questions about, since we have a way to be able to kind of discover, so use a little bit of data to build a machine learning-ish kind of model that is also an epidemic model, right? This hybrid routine between them. What are the things that we can do with such a model? Now, one of the things that we looked at is how robust is this to actually working with small amounts of data, right? So what we could do is we could take 5 compartment models and 9 compartment models and actually just see, right? Can this 3 compartment plus quarantine-ish kind of model, can this capture the behavior of larger and larger epidemic models, right? So we work with Sandia National Labs and actually just checked a lot of these, larger, epidemic models with things moving in space, et cetera. And it turns out that this QSIR is able to, right? So it's able to train on, on a very small amount of data and then extrapolate in a way that is fairly realistic, right? And this is that property that, the model has a lot of the dynamics that you would expect of an epidemic model. It just is learning a little bit of the nonlinearities in there to be able to make it kind of work for a given data set in a way where standard machine learning methods just don't, right? So, the red line, the red is where we train here. The purple is where we extrapolate. You can see that this extrapolation does not work well if you do not try to have some of this prior information about, mechanism of the epidemic, at least for the amount of data that we're giving it, right? There is a level of data that you need for this thing to work. And we found that, around 30 days or 30 data points ended up being what was needed across a different wide set of models. So this is actually something that we'll be publishing soon, just like a full study of, for this kind of scientific machine learning, what are the data requirements and how do you make it fit more robustly? So that'll be one to kind of watch out for. But with this in mind, right? Knowing that knowing kind of what the data limitations are required, and establishing that the more model you include with the and here we establish that with more model you need less data. With less data you need more model to predict well, right? With those things established, we then started to try to look at whether we can use such a QSIR idea to compute something that is actually truly interesting for epidemiology itself. So one question that came up then was a counterfactual, right? Because at the time we were doing this, a lot of the U.S. southern states decided to stop enforcing the masks. It was in the summer of 2020, right, July of 2020, and infection counts were starting to go down in the U.S. and everyone thought, well, let's just open up, right? Well, not everyone thought that, but a lot of the southern states did, right? So this leads to a counterfactual, right? If the southern states did not open up due to COVID, right, there would not have been that major second wave that happened in the United States. How much of the cases can we actually attribute to the policy? And it turns out that this kind of modeling mechanism can give you a way to look at that counterfactual, right? Because we have an epidemic model that extrapolates well, that has in there something that really captures quarantine, right? When we go state to state to state, it really is capturing when the quarantine levels were going up and down. And in a relative sense, it has numbers that are, to a given region, its numbers are predictive, right? And so, even though the absolute number of Q of T might not be something that is interpretable, what we can still do is do a counterfactual and say, what if at the time when they changed the quarantine levels, right? What if they did not actually change it? What if they actually kept it constant? And if you do this, right, it's kind of interesting because you can actually see at that time, from the QSAR, that if you actually train it on the full model, it actually will show you that the quarantine was dropped at the times when we know it was dropped, right? If we back it up and say, what if that did not happen? We can actually then calculate, state per state per state, what the mean, case reduction would be, and be able to really quantify then, like, this is the true effect that the policy had on this area of the United States. And so, this is something that we're then able to, kind of match against other people's quantifications. And this is something that seems to be matching up quite closely. And so it's quite nice because this is almost a very, semi-automated machine learning-ish kind of way to get to a very deep counterfactual question and kind of ballpark it quite quickly using this idea of, well, let's machine learn plus epidemic model and let the training process take care of a lot of the details, right? And one other thing that we looked into here was, well, if we wanted to just say that we don't have many details about these epidemic models, but all that we have is we know the graph connections, right? So we know that susceptible people turn into infected, and infected turn into recovered, but infected could also be hospitalized, right? If we only know, the connectivity of this, can we actually recover what the terms should be, right? Can we recover which terms are quadratic and which terms are linear? And it turns out that you can do this, right? If you do this training where you have these multiple neural networks, you do this weight estimation, and then when you do that, the sparsification at the final step there, you actually recover the correct forms of the equations. Now, this does require a certain amount of data, and then we in the publications we go into how much data is needed for these kinds of things. But what we do showcase in this case as well is that this sparsification does not work without imposing the epidemic structure, right? So it really turns out that by giving it the structure, saying like only susceptible can turn into susceptible can only turn into infected, that really constrains this learning process to make it so that way even small amounts of data are able to give you something fairly accurate. And then when you sparsify it, it actually gives you back the same forms of the equations you started with. So one way that we're actually starting to try to make use of this in practice is actually a project with Yoni, which had been featured on Gizmodo and such, where Yoni had this great idea of you can create these virtual strands which would be moving across between users on a cell phone, and if you then have this, you have a proxy for what people's epidemic model would be, right? You'd have a proxy for who's spreading to who in a way that kind of captures social network data. And so if you have that, then you can, that's what we call the safe blue strands, these light blue strands in the background here. If you have that kind of information, then you can use that to kind of recover what the dynamic model should be given the amount of infected cases in the past. And if you know the relationship between the infected strands to give you a dynamic model, right? Once you've learned a predicting dynamic model from how to read out the strands from the cell phone and how they're spreading, then you can predict in real time what the future should be, right? And this kind of solves an interesting question in there, that we know that epidemic statistics lag, but this could give you something that is a fairly good predictor, in real time. And whether this actually works in practice, this is actually being run with an on-campus experiment. So we'll actually find out fairly soon how well this kind of SciML in real-time prediction does work out. So that is something to stay tuned for. So that's the part of the talk which is all about how scientific machine learning is being used within epidemic models. Let me then take a step back to the mathematics and talk about, how is all this fitting process actually done, right? Because it's kind of been a black box. I just say you train the neural network inside of a differential equation and you turn it into symbolic equations. But that needs explanation, right? So a lot of this is done with the SciML open source software organization, right, which has these tools like differentialequations.jl and such, which a lot of people may know. So the foundation of the tools is what you need first is fast differential equation solving. Because if you're going to be solving differential equations for inference, you have to do it thousands of times. If you're going to solve differential equations for inference that have neural networks in there, well, then you're going to solve lots of expensive equations thousands of times. So it better be a very fast process. And so, I mean, if you've looked at the benchmarks of the Julia differential equations.jl suite, it generally benchmarks at around 50 times faster than SciPy, 50 times faster than MATLAB, and 100 times faster than RSD solve. There's a lot of benchmarks you can find on the SciML benchmarks.jl that go through all the different cases, and a lot of these papers explain why this is the case. There's a lot of engineering details that thoroughly explain each part of this, each part of these accelerations. And it's one thing to kind of bash on Python, MATLAB, or R, right? Because they're slow and easy to beat. The real core of the differential equations suite is that they tend to outperform a lot of the classic cases that come from Fortran and C as well. So, for example, here you have the QNDF solver, which is which is able to solve 1,000 stiff reaction equations in a time that is faster than something like CVO to ePDF, even when we are giving it the advantage of using our special Julia-based linear algebra, which is specializing for people's CPU cores. If you don't give it our linear algebra, it's actually the one all the way up here, and there's about an order of magnitude difference, right? And this is actually excluding some of the recent advancements that we have, such as an extra 2x from symbolic tools that automatically read your equations and transform them into a form that has the minimum floating point operations, and a 2x from sparse parallel compilation, where it can generate it can read your code and then generate the it can generate the analytical solution to your Jacobian. It can then turn it into a sparse matrix because it would know the sparsity pattern, and then it can automatically turn that into parallel code. So we thought that was kind of cheating to have this in this graph. So we didn't add the extra half an order of magnitude, but these papers right here go into those details about how that's all done. Right. So this is kind of the foundation behind this universal differential equation approach. First of all, you just make sure that you can solve differential equations very, very fast. And this was kind of like a 5-year project to get there that has all the details for other reasons online. For the symbolic simplification, we built out this new library, symbolics.jl. I think that the best benchmarks are ones that come from real users, right? So someone from the robotics domain picked it up, and he was trying to do something for 20 minutes with SymPy, and then while the SymPy was still doing that computation, he picked up symbolics, learned the library, and then it was able to do the simplification in 1.5 milliseconds, right? So this is a pure quote, just kicked right off of the Slack, because it was a nice one, and we actually enshrined that now inside of our benchmarks. It is a 2,370x speed up from SymPy that shows how you can generate mass matrices for differential algebraic equations because of some different forms in the way that it basically has a lot of simplification by default by using operations in a way that's stored in specific hash tables. And those are details that go for the ACM computing talks. But So this is really the core then is a fast symbolic engine with a fast differential equation solver, and then it's all pieced together. So basically what you can do in the system then is you can define systems in a symbolic way. So you can say, here's my PD constraint optimal control problem. You can describe it fully symbolically as a symbolic PD. It generates symbolic ODE systems, which then generates optimization systems with symbolic ODEs inside of there, and it does the whole code gen process to make sure it's sparse, parallelized, and all that. Then it runs it through the fast differential equation solvers, and it has a process for it's automatically doing automatic differentiation and generating adjoints. And really the key for how this got fast is that this pipeline is using about a stack of about 200 packages, which has had over, I think at this point, like hundreds and hundreds of different developers throughout the whole stack. And so it's been optimized in a very nice way to be able to use everyone's work instead of trying to recreate the wheel for every little detail. I mean, at this point, there's even, as I mentioned earlier, there's even pure Julia Blazes, so that way it doesn't have to rely on older Fortran ways of doing the linear solve, which have been beaten out by things like loop vectorization.jl. So you could look at the benchmarks of every single piece of the stack and see, oh, this gives you this X speed up, this gives you this X speed up, and then when you start to put things together, then you start to see where all this comes from. So how do you actually do the fitting process? Well, the fitting process is fully automated. If you just say, here's a differential equation that I want, here's a differential equation in the differential equation.jl syntax, I want to solve it. If you just put this inside of a training loop for, say, a machine learning library, it just generates all of the methods for forward or adjoint sensitivities, which is a very interesting topic of itself. But before going into that, let me just kind of show what that looks like. So you define the ODE. Here we just define an ODE, and inside of that ODE, there is a neural network. And then we put this inside of the training loop. It automatically knows how to generate the adjoint equations, where inside of the adjoint equations for the ODE is running the backpropagation. And so this is actually what it looks like in real time on my laptop, right? It's just something that is fitting. You're able to fit these things within seconds then, and really able to iterate and try a bunch of different methods. Right? This is like this is the true real-time runtime of what it is. So what were the keys to actually getting it so that way it runs, parameter estimations of thousands of parameters run at that speed? Before getting there, so diffeq flux, one of the nice things about it is that what I showed there is what's known as the single shooting method, right? Where what you say is, my loss function is solve the ODE, and then from the ODE solution, here's how I define a cost function. There are multiple different ways that you actually want to make this system more robust in practice, right? So for example, a multiple shooting method, you don't solve from the start all the way to the end. You solve in little intervals, and it turns out that improves your solving. Also, a very recent paper in statistical applications in genetics and molecular biology that we did, it goes over a collocation method where by fitting collocation polynomials, you can generate derivative information, and you can do direct fits of derivatives. And so this library really has this way of letting you combine all these different estimation techniques and generate fast derivative terms. And so I'll skip over how this interacts with stiffness. If someone wants to ask questions about it, please do. The reason why I'm skipping over it is because I've given a full online talk on that topic. So if you're interested in how is this robust to effects of stiffness, and how do you make stiff neural ODEs actually work, you just please check out this talk, Scientific Machine Learning and Stiffness. The interesting thing about this topic, though, is that using a stiff ODE solver is not enough for actually making neural networks inside of, neural networks trying to train a neural network on data from a stiff ODE does not work just by using a stiff ODE solver within this process. You need to change the way that your gradients are actually calculated, because you need to make sure that the gradient process is a stable solve itself. And that's a whole talk of its own. But one thing to mention then is that this is all stiff to robust to stiffness, which is one of the things that was required to make it really work inside of the epidemic modeling domain. And now that, as I mentioned, there's all these packages that piece together. The package that actually does the core rewrite. So when you call it to do, when you tell it to do a solve training, what it actually does is it has a whole bunch of different ways that it can generate it actually writes down and generates the code that would be the code for forward or adjoint sensitivity analysis. So what I mean by that is, when you call this training loop, it actually looks at this function and it generates a new function that should be called whenever the gradient would be called. And there's each machine learning paper, or also a lot of the classic control systems papers, they have kind of detailed these different ways of doing these grading calculations, and it turns out that they all have different properties. They all have different properties in terms of memory usage and performance, and so we have really put together this combinatorial matrix of all the ways of putting it together. Now, one little detail which is very, very interesting in this space, though, that it works on is, when you actually are trying to solve the adjoint equation, one thing that a lot of people kind of miss is that, so here's the adjoint differential equation. So the way you calculate these derivatives is you solve an ODE forwards, and then you solve this adjoint equation backwards in time. And now, this thing is defined by the Jacobian, and then you transpose the Jacobian and multiply it by this lambda term. And turns out that actually doing this calculation as written is not a good way to do it. It turns out that if you were to instead look at this as a vector Jacobian product, this is the primitive of reverse mode automatic differentiation, which means that the way to be able to calculate a vector Jacobian product is actually to put into your original ODE function, or if your ODE is a neural network, put into your neural network the value of u, and then you tell reverse mode automatic differentiation to pull back the vector lambda. If you do that process, it actually is equivalent to a vector Jacobian product, which means if you've ever done the back propagation derivation before, right? You get to the very end of the neural network, and you stick 1 in, and you back propagate 1. It turns out that backpropagating 1 is equivalent to calculating the gradient. Backpropagating lambda is equivalent to calculating the vector Jacobian product with respect to lambda. So actually, the way that we do the adjoint differential equation is using the neural network backpropagation in the definition of the generated reverse ordinary differential equation. And this changes the computational cost quite a bit, to the point where it's actually about a two order of magnitude improvement on realistic equations, like on this Brusselator partial differential equation, right? So a lot of previous tools, like those from C, if you kind of keep your automatic differentiation and your differential equation solver library separate, you cannot necessarily do that trick, right? Because this trick requires using backpropagation within the way that the differential equation solver is generating its adjoints. And so, really trying to piece all these things together so that way the machine learning and the numerical analysis, right, not just in the modeler's part, but also in the software, really combining all the techniques, gets you something that is that really gets you the rest of the speed gains. So the SciML ecosystem is really the only one that has all the things that are required for robustness on stiffness, along with this adjoint generation technique that is then also compatible with GPUs and everything that's needed to do the examples that I mentioned at the first part of the talk. What does that actually mean in the end? Well, if you take something like torch-stiff EQ and you check its efficiency against these methods, you can see that there's usually more than an order of magnitude difference because of these finer semi-engineering plus numerical analysis kinds of details, right? In fact, the difference in training a neural ODE is so different that the time it takes for the time it takes for DiffEq flux to do the full optimization of the neural ODE that I showed in the animation, that is the time it takes for torch-stiff EQ, this PyTorch based library. That's the time it takes for it to do one iteration, right? These kinds of fine details may not matter for some people, but in the end, as this kind of is trying to popularize and you're trying to make sure that these methods can be more widely spread, that kind of difference, 2 order of magnitude difference in speed is really what we're seeing is making more and more users really be able to adopt these kinds of techniques. And so we've really, these techniques and the speed has really kind of changed some applications. I'd point to Johnny Diegelman's talk where he's from NASA Launch Services, where he saw 15,000 times acceleration by switching from Simulink to these modeling toolkit.jl and this whole simulation stack. We showed with Pfizer's quantitative system pharmacology team a 175x acceleration on their preclinical models in 2020. And probably the one that it has the most claim to fame here is that the software stack then had a different had a different way that it impacted the pandemic, because it was adopted as the go-to tool by Moderna Therapeutics in 2020. And so this is one way in which computational efficiency and the ability to do parameter estimation and model estimation really fast can it can lead to scientific discoveries in a way that is pretty game changing. So yeah, thank you very much. This hopefully kind of goes over both how this was used in epidemic modeling, but also like a very quick behind the scenes of this what is actually going on in the software and how it's being used, and what scientific machine learning is actually doing to this to change the field of this numerical differential equation software. So thank you very much.
Thanks, Chris. It was a really interesting talk. So any question? We have like 10 minutes to ask questions, and you have feel free to discuss.
Hey, I'll maybe start. Thanks, Chris, for the great talk. I have a general open-ended question first for people that, some people here that are listening, I know use Julia, but many others still don't. Can you outline a bit the learning curve and kind of the best path to enter and start to use this ecosystem of SciML in Julia or otherwise?
Yeah, I mean, I would point to the nice thing about online talks is I can show all the stuff, right? So one thing that I would point to is that if you're interested in using like the differential equation solvers and doing differential equation modeling, I would say intro to differential equations.jl. It should just pop right up. Yeah, this video for back when. It still has a the same syntax and everything, and it goes over a lot of different details, like how do you define models, how do you do events in your model, so how can you make it so that way you have discontinuities and such, how do you optimize your code so that way it runs fast. Some of the details on the code optimization are now actually more automated than they were before, so you don't actually have to do as much work as I mentioned in the video, but this is one nice way to jump right in. If you go to diffeq.sciml.ai, you'll find the tutorials, and you can jump right into the first tutorial is just a linear ODE, and then it goes into how do you do larger nonlinear systems and such. So all the tools. I mean, if you haven't used Julia before, I'd just say search for something like if you just search for differential equations Julia, the things that you're looking for will pop up. It has literally thousands of packages. I think it has over 6,000 packages at this point. So if you're looking for something, it's probably already has a package.
Thanks. And just a follow-up small question. I know that you've wrapped some things in R. Not everything is wrapped in for R or Python, right? Or just a subset, or just differential equations.jl, or?
Yeah, well, I mean, so differential equations.jl along with modeling toolkit.jl is wrapped in R. I actually have a blog post that showcases that you can do GPU accelerated ODE solving in R using this stack. And I forget what the final performance. Yeah, so it gives about a 2,777x acceleration over DE solve when you use this from R. I mean, it's using Julia for doing both a JIT compilation and it's doing a GPU kernel generation process for reading that number. If you don't do the GPU generation step, I think you only get to the 350x, but it's still a nice it is a nice process, and this blog post goes over how do you make use of it and such.
Thanks.
Yeah, the Python package also exists, right there. So this is diffeqr, which you can find. There's also this Python version of it, though the Python version has not had as many performance optimizations. I mean, Python is a pretty nasty language to actually engineer on, right? So it just isn't compatible with a lot of the JIT compilation stuff yet. So at some point, we will try to get a limited version of the JIT working from there, though.
Thanks.
Yeah, can I ask a question, Hamid?
Yep.
Marcus here. Christopher, thanks. That was a really interesting talk. Lots of amazing stuff. I kind of wanted to ask about the first part of your talk, really. So this whole idea of using neural nets to kind of do function approximation as part of a DE model. What kind of, are you just using sort of small MLP networks in there, or what are the details?
I mean, it depends on the problem. A lot of times it is just an MLP, right? Because what you're really trying to use it for is just the universal approximation theorem, right? In some cases, if it's a low enough dimensional object, you could do something like, oh, let's just say we want to use a Fourier series or a Chebyshev series, right? Like what you're really looking for is something that approximates well, but is also numerically stable. So just saying like, oh, it's an arbitrary size polynomial, actually that does not have good numerical stability properties, and it leads to a lot of local minima, right? So one of the nice properties with neural networks is that they do, have this property where if the neural network is large enough, then your local minima end up converging to being all similar global optima, right? I mean, it's similar in the sense of function, right? The parameters are different, but the function that is approximating can converge, right? And so there's some nice theory that say, neural networks can work well here. And so, if it's a small enough dimensional object, yeah, go ahead, use a Fourier series and whatnot. But as the dimensionality grows, then some of the examples make more and more sense with the neural network. So some of the examples that we're looking at with like 9-dimensional objects, right? Using a Cartesian product of 9 by 9 by 9 by 9 Fourier series, it has exponential growth in the number of terms you need, whereas a neural network just doesn't have that cursive dimensionality. And that's the reason to use the neural network. Though in the library, knowing that there are these use cases where you might want to use more classical function approximators, there is a whole setup for that. So there's this whole tensor product layer where you can tensor between different objects. And there's these pre-built different classical bases. So Chebyshev basis, sine basis, cosine basis, Legendre basis, etc. For being able to mix in those types of terms.
Okay. Yeah, I mean, I'm a machine learning guy, so I feel a little strange here about kind of almost being anti-neural net here. I mean, I guess that's okay. But what you kind of did after that was took the neural net and then sort of, as if you were seeking to get a nice explanation of that by fitting a polynomial or something to the neural net's inputs and outputs. So why not just directly apply the simple interpretable model and do symbolic regression or something like that?
I mean, that is definitely the great question to ask, right? So why would you not just take a model that is covering over, like, oh, we can have polynomials that go up to cubic, or and just stick every single term and do an approximation like that, right? The reason, and this is something that we had tried for a long time, and this is the process that we did before machine learning integration, right? The difficulty with doing that is that you have a lot of local optima that show up in those kinds of models. If you actually take a look at the loss function spaces, I don't know if I still have this in the documentation, but if you look at what happens in your loss function spaces when you do that, you end up getting a lot of local optima. And so you have to switch to using derivative-free global optimization, and it really becomes a really messy process, right? It just turns out that using a function approximator that is over-parameterized does give you something where the local optimization has a much better chance of giving you a good local optima. The other part of that is it's hard to know how to do the mixture of sparsification with it's hard to know how to do the mixture of sparsification with the fitting process. So here, for example, is just the one parameter log likelihood when fitting the parameters of the Lock-Volterra equation, right? It's just a simple nonlinear ODE, and you can see that simpler ordinary differential equations actually have more pronounced local minima. And so as you try to actually simplify your forms, it actually becomes a harder and harder and harder optimization problem. And so it's kind of counterintuitive that putting the neural network in there makes it simpler. So you kind of use a simpler optimization problem, and then doing sparse regression of a neural network down to symbolic forms is also simple because it's a problem that's been looked at in other ways. And so it's turning a hard problem into two simple steps, and two simple discrete steps that then solve it pretty straightforwardly.
Okay, that's really interesting. Thanks.
All right. Thanks, Chris. So
let me throw one last thing in there, though. Right?
Yeah. Okay.
So to modelers, I usually say that, this is the skeptic's form of machine learning, right? Now, the way that I usually explain it to machine learning people, though, is a little bit different, right? In that, when in machine learning, right, when you think about something like a convolutional neural network, right, the reason why it became it works so well is it has inductive bias, right? That inductive bias is that it keeps this idea of spatial locality, where the only things in the convolution is that it only allows you to work with things nearby, right? And a recurrent neural network has this inductive bias of time series, right? What we're really doing with this form of scientific machine learning is we're putting generic inductive bias with respect to epidemic modeling, or generic reductive bias with respect to the known physical equations that we have. And so this is kind of another way of getting to this way of thinking about SciML.
Thanks.
Can I ask another question? So I'm a modeler. I don't know too much about machine learning. My question kind of, I think, relates to what Marcus was going to say. As I understand, so we assume we have an incomplete ODE model, right? With some unspecified terms, some nonlinear terms, and also some parameters which may or may not be fully known. And then, so I guess instead of parameterizing simply these missing terms, so you try to come up with some sort of neural network representation of the missing terms. So in this case, the interaction terms in the SIR model. So the question I would like to ask, when do we know? So clearly, in order to complete the model, you need some data to train your neural network. So the question is, when do we know that the data is just, is there any situation when the data is just not enough to provide useful prediction? Because once you open up to, so you have missing parameters even in a fully known model, then or not fully constrained parameters. Then if you would, let's say you could have some parametric form of the missing term, let's say adding some power of S and I, that would be again still parameter fitting. But if you open up to arbitrary functions, basically you give lots of freedom to the model to have all sorts of functional forms that the neural network can represent. So then basically you have a limited amount of training data, but you allow your model to get around in a pretty broad space. How do you know that the data is sufficient to constrain your model in a useful way? Or another way, the problem, what I see is usually the problem with this type of models is that it's hard to validate things. You don't really know what would be the future without, so kind of it's easy to, okay, I can come up with a model that replicates the data, but maybe that's not a unique model. Maybe there are hundreds of these type of models that would produce the same data. So kind of would be good if there was some criteria when you could say, okay, this data is not enough, and the model cannot be kind of completed with useful terms, or kind of what you think about it.
I mean, that's a great question, and we're looking to try to solve it. I mean, that's what I was saying. Like, the one of this next papers that's coming out, we did do a study on the data efficiency and everything. So we were able to kind of say, like, oh, you know, we were able to kind of show that on the harder and harder, you know, versions of epidemic models, if we're then trying to turn them into simple, you know, QSIRs, you know, just a SIR with a Q in there, right? How much data do we need to be able to learn a model that is sufficiently extrapolating and such? We were able to kind of show that the general properties are true, right? That the more model you assume, you know, the more model that you assume and the more model you assume correct, then you're able to extrapolate better, and the more, you know, it is able to do better than the neural ODE, and you know, and so, you know, and it is able to do this with, you know, a small amount of data points, like something like 30. But what we were also looking for in this is, you know, is there some kind of numerical number where it can be like, if this number is greater than 1, then you can trust the extrapolation. And we haven't been able to find that yet. That is definitely one thing where, you know, so we can show on simulated data, you know, where we know the truth that, like, hey, A, we're able to get, you know, the right equations back, and B, we're able to find other forms that extrapolate well and such. But we do know that, you know, there is an amount of data that you need for that to be true. We do know that, you know, as you assume more of the physical form, that data requirement goes down. But we don't have a nice way of saying, for this amount of you know, for getting this amount of the mechanism correct, you need only this amount of data. That would be the holy grail for the approach, and we have not gotten that. So yeah, that is one of these things that we're trying to find. You know, if we're almost trying to find it experimentally at this point, right? If you run this on tons and tons of different models, is there some kind of diagnostic that's coming out that's, you know, similar to AKE information criteria or something? But we're not finding the right thing yet. So that is definitely the right question to be asking here. Yeah, because we can validate it on simulated data and then go to the real data and say it should work because of this, you know, what we show over here. But there is a jump, and that we do need to find the right way to be able to verify it better than that.
Thank you.
All right. I think, yeah, I'm sure there are many questions, but definitely we can discuss it later or through email. So thanks, Chris, for joining us. Yeah, we will meet later. Thank you.
Yeah, thank you very much for having me.
Chris.
Yeah. Thank you.